you want to get to a point where you're starting to develop a little bit of an intuitive understanding of them, right? So basically, what an iteration is you plugging a number into a formula, getting a result, plugging that result back into the formula, getting another result, and repeating the process over and over again for some predetermined number of times, or until you reach some predetermined goal. Right? Newton's method finds successive approximations for the solution of f of x equals 0. So it's basically another way to find the zeros of a function, and it's actually the way the calculator functions with that. Basically, when you do the zero function on your calculator, it's applying Newton's method. So I think that's pretty cool. But what we're doing is we're finding the ratio of the function at a point to its derivative and subtracting it off some particular x value. Right? So the program will walk us through that, but the iterations should get closer and closer. The results of the iterations should get closer and closer to the true, whatever it is. In this case, 0. But we could also use it to solve systems, which is a pretty cool application of it. So I'm just going to walk you through a guided example, but after we put the program in. All right. So program. We want new. So program right arrow till you get to new. And we're calling it NEWT. So our alpha lock is on, and E W T. Hit enter to lock it in. All right, so now the title is established. If you screw it up, if you messed up the title at this point, quit out of here, create a new program with the correct title, and then later on I'll show you how to delete a program. Because it's actually kind of a pain. That's like the one thing that's tough to edit in a program is the title. Everything else is it's actually too easy to edit, to the point where you accidentally wipe out lines of code, which is not a good thing. All right, so I want to display initial guess. So, you know what? Actually, I'm going to add in a line here. So let me lock on my, well, yeah, because this program requires you to have put in the function for y1 already. So I would want the person to know that, right? So let me do program IO, still display. So option 3. And then I'm going to put a string in here, so the quotes, so alpha plus for the quotes. And then I'm going to say equation, you just do shorthand, equation, EQ, in, the space is 0. So alpha 0 brings the space in y1. All right, I'll turn off my alpha for that because I'll do my alpha trace. Well, actually, I need alpha anyway. Alpha trace y1 question mark. So alpha negative sign, close it up. Not necessary. If you don't want to put that in, you don't have to put it in. I just think it's a nice reminder because if that comes up when you run your program and you realize you haven't put your equation in, quit out of the program, put your equation in, and then go back and run the program afterwards. All right. There's other ways to do it. Some of the other programs that I have and the ones that we've done have coding for that, but well, we're not going to do it that way this time. So now we'll start here. And by the way, I'll take this as a typo if somebody wants to submit it. Program IO, so new line of code, display initial guess. So alpha lock, so second alpha to lock it on. I'm about to type in a bunch of stuff. So then plus initial. You can abbreviate in any way that makes sense to you because this is your program. If you want to go init guess, whatever, it doesn't matter. Initial guess. You already screwed it up? Already. Like catastrophically? You hit clear? Oh, that's like the worst thing you could do. Alright, so initial guess, then we're going to input X. So enter to get into a new line, program, IO, input, option 1, value X. Sounds like a typo coming in. Felt that vibration. Now, this one I think is new. Maybe. I don't know. I don't know if we've done this yet using the LBL, the label function. So it's under control in the program menu. Finding it isn't the challenging part. I mean, if you go into program and look around hard enough, you find what you're looking for. And if you can't find it in the program menu, go into the catalog, because everything's in the catalog. But we're typing in label 1. What this is an anchor in the program. So later on, you see in the very last step, it says go to 1. What that tells us is we have a conditional that needs to be satisfied. If X is not equal to A, then we go to 1. Program, then you're in the control menu, so just keep scrolling down until you see LBL. All right, so what'll happen is, because the calculator is weird, the conditional sentences, we have if, but there's no then, because the next line of code is your then. So if that conditional is satisfied, then the program knows to go to the next step. If it's not satisfied, I just want to make sure I'm saying that right. If X is not equal to A, then we're repeating the process. Okay, so if that's satisfied, we go to the next step, right? So that's the follow-up of our condition. If it's not, then the program just stops at that point. All right, and you'll see a done message. All right, so what I'm going to do is I'm going to store X into some dummy variable. So my X, STO, the store key, store it in as A, just so I can compare the value later on, because X is going to get replaced with a new value down the line. And so X is always going to be changing. I want to know, I want it to be reported somewhere what X was before I started the whole process. All right. So the next line, X minus Y1 divided by Y4. This is the Y1, Y4 that's in the alpha trace menu. Right. So these instructions refer like old calculators, TI-83 and older 84s. So maybe they're in updates in order. So I'll take as a typo that the 1 and the 4 should be subscripts, and I'll take as a typo that this should say alpha trace Y1 and Y4. All right, so X minus alpha trace Y1 divided by alpha trace Y4. That result stores in for X. All right. So the Y1 is where your original function is going to be. The Y4, we're going to set our calculators up if we haven't already done so, for the derivative to go in there. You should actually already have that, but if not, we're going to do it together anyway. Those things need to be in place, but then this ends up being Newton's method, because this is really the same as saying X minus f of X over f prime of X. Right? It's just written in a different form. So then I would display the X value, so program IO option 3 X. Then I pause. All right, so program control, you just look for the one that says pause. I think it's just after the 9. Oh, actually, it was an 8. So program control menu, and it's option 8. And we need a conditional. program if, and we establish our conditional. X is not equal to A. So in the test menu, second math, we have all of our equalities and inequalities. If X is not equal to A, then we go to 1. So program, control, and we're looking for go to.
Something using alpha stores my X, is that right?
Yeah, it's the same X. Yeah. You know what? Somebody in my linear algebra class showed me a trick, and I think it might apply here. I think it was under Markov chains. I'm afraid that I'm going to screw it up and therefore make it way more confusing than it needs to be. So I'll try it out on my own, and if I can take some time next class, I'll show you the adjustment. But anyway, it's in, program's in, quit out of here. Running the program, it's not difficult. You just need the original function in y1, so we hit y1, or we hit y equals and go to y1. I'm typing in this function, x cubed minus 3x squared plus x minus 5. All right. I'm going to clear out my y4 and take that from scratch just so you get a refresher on how to do that. All right. So the y4 should be the derivative of y1. All right. The notation here again is for the old calculator. So again, we've got typo bonus opportunities everywhere. So that's good for you. It's a win-win for everybody. Right. So definitely take advantage of those. Math, option 8 is numerical derivative, but it comes up like this on the 84s. X on the bottom. We're pointing to y1, so alpha trace y1, and we want it for all x. I always have my y4 bolded so that I can see the difference between the two graphs very easily, but we're not really looking at the graph here, so it doesn't matter. We can turn off the equal sign, hit enter on the equal sign for y4 so that, we don't have to worry about that leading to an error message at some point. All right, so I have my equation in. Let me quit out of there. I'm going to run the program. Program NEWT, hit enter. It's in the execute menu. Enter, enter. First thing that comes up, equation in y1. Yes, I did indeed put my equation in y1, so I'm pretty comfortable that I didn't botch it up before I even got started. This problem is telling us the initial guess should be 3. Now, your initial guess could be anything. It may take more iterations for you to get to the final answer if you start off farther away from where you're supposed to be. So type in 3, hit enter. All right. I get that value. Then hit enter again. I get that one. Enter again, enter again, enter again. Keep going till it says done. Once it says done, well, it's done, but the reason why it says done is because 2 consecutive iterations led to the same value. Right? So the program didn't get past a line of code that said if x is not equal to a, right? Because the conditional on that was saying if x is not equal to a, then go back and start the process over again. Well, x is equal to a, so the program knows to stop at that point. All right, so these 2 values are the same, which means that this is my solution. All right, so if I'm looking for roots So this function, I now know that one of them is about 3.17 whatever, 17998, right? But what I would do here is count up the number of iterations it took to get there. 1, 2, 3, 4, because the fifth one is just a repeat of the fourth one. So the way I would phrase my answer would be to say the solution is, well, the whole decimal, 3.17, all of that jazz, after 4 iterations with initial guess of 3. All right. So, had we been learning about this as part of the regular curriculum on a test, if this question came up, that's all you would need to do. You tell me what the solution is, you tell me how many iterations it took to get there, and then that would be really it. As long as I know the initial guess, I can verify your work. All right? So, your assignment, I have another, another solved example here that you can follow through. But your assignment is to just use Newton's method to figure out solutions. All right. So this part of it is what would go in. All right. I would want a decent window. So I go into my y equals, I put my function in, x cubed minus 3. We want a good window, so I'll start with a zoom 6 and see if that's good enough. That looks all right. If that's the case, then all you need to do is just give me a quick sketch and just tell me what your window was. I put extra stuff in here that I really don't need, but sometimes people mess around with some of these settings. But really, if you didn't mess around with scales or anything like that, then all I need from you is the x min, x max, y min, y max. So negative 10 to 10, negative 10 to 10. It's only for like trig problems that you need x scale, y scale. Resolution you almost never need. So now that we have the equation in, we run Newton's method. Program NEWT. Initial guess. Well, that's where you come in. Right? So you take a look at it, and you see, well, it's in the neighborhood of 1 to 2, right? If I'm looking for an x-intercept. I don't know if it's precisely 1.5, but I'm going to guess that it's 2. Maybe you guessed 1. All right? So then what I would do, I type in the 2, hit enter, 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 and keep going until you get it done. All right? So then these values, and this is the part that you're not going to like. I mean, maybe you don't like any of it. I don't know. But these values get popped in here. You can do some rounding. You know, you don't have to put the entire decimal, but maybe like 3 decimal places. At least, or maybe 4 in this case, because it doesn't take too long before 3 decimal places end up being not, a distinguishing factor. All right. Now, this is a cubic function. Cubic functions could have as many as 3 x-intercepts. So normally I'd be on the lookout, but all the twists and turning happen for negative values of y. So I'm looking at this graph saying that there is only 1 x-intercept, and I'm good to go there. All right. We know algebraically what the answer is supposed to be. You just add 3 and take the cube root. It's actually the cube root of 3. But the whole point behind this is to come up with a reasonable estimate. So x would be 1.44224957 after 1, 2, 3, was it 4 iterations? or 5 iterations, because I didn't copy the last one. 1, 2, 3, 4, 5. Yeah.
Is there a way to stop your program?
Hit on. On to interrupt.
And quit?
And then quit. Yeah. All right. So give me the number. Tell me how many iterations it took to get there. And then that's all I need, because your table should have the initial guess anyway. We don't need to repeat the process. It may seem like overkill to write the 5 iterations, even though I'm listing 5 iterations here. But you see the table only has 5 values. If you go through Newton's method and hit enter, 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 you keep hitting enter, going through those iterations. Some of them, it'll take like 30 or 40 iterations before you get there. Right? I don't want you to have to write 30 or 40 decimal values. I just want you to write the last 5. All right? But it should be an appropriate number of iterations. So you're keeping track of how many times you hit enter as you go. But just, I mean, I don't want you to have to hit enter, write it down, hit enter, write it down. You'll be here forever. So hit enter 1, 2, 3, 4, 5, 6, 7. Got it. And then just give me the last 5.
Is there a way to like scroll up and see like stuff inside the program? Because if I was to run it and then I'd go on to another thing, but I could scroll up and find like see if there's ways of just say program maybe.
To the best of my knowledge, no.
So I have to see the equation for scrolling.
Yeah. So, but that's the gist of the assignment. So I did this one for you, so you should have this answer. Of course, I did like the easy one, but you know, that's my prerogative. I'll take you through, or at least get you thinking about number 3, because it's a system of equations. If we're talking about a solution to a system, we're talking about where the first equation is equal to the second one. Newton's method requires one side of the equation to be equal to 0. So what I would do, anytime I have a system, set them equal, but then move everything to the same side. So this is the same as saying sine of x minus cosine of x equals 0. And this is what would go in for y1. All right. So that's really all there is to it when it comes to, or at least not all there is to it, but at least it addresses the distinction. So what makes this different from what we were talking about? It's just taking the two parts and basically subtracting one from the other. All right, but then everything else is the same. Same idea here. This one you have to solve for y first, so that's fun. But that's that. All right, so let me start this.